Hello and welcome to Dynamo, the dynamic programming tutor. My name is Martin and this is my honors project for the University of Edinburgh. I'm going to give you a quick introduction to dynamic programming and then we will continue with a tutorial on how you can use my system to solve dynamic programming problems. Okay, so what is dynamic programming? Dynamic programming is a technique for solving complex problems by breaking them down into simpler subproblems and then recombining the solutions to the subproblems to find a solution to the initial problem. Okay, so what does this mean? This means that we have this really big problem, and what we're essentially doing is that we're breaking it down into subproblems, like this. And then these subproblems, we can subdivide them even more, and we've got these teeny tiny problems over here. Okay. And then again here. So the algorithm would first compute the solutions here. Then it would go on and compute the solutions here. And then finally it would go on and compute the solution to the biggest problem, which was our initial goal. So what happens in practice is that these teeny tiny problems, they often overlap. So it could be the case that this problem and this problem is the same problem, so we don't need to compute this, and in fact we only compute this. Okay, so let's illustrate this with an example. Okay, so we'll be illustrating dynamic programming with a problem on the Fibonacci sequence. If you're unfamiliar with the Fibonacci sequence, it's defined in the following manner. So the first number in the Fibonacci sequence is equal to 1, and then the second number in the Fibonacci sequence is equal to 1, and then each consecutive number is equal to the sum of its two predecessors. Okay, so yeah, for example, we get the sequence 1, 1, 2, 3, 5, 8, 13, 21, and so on. Why? Because 3 is equal to 2 plus 1, 5 is equal to 3 plus 2, 8 is equal to 5 plus 3, 13 is equal to 8 plus 5, and so on. Okay, so let's see how a depth-first approach would calculate Fibonacci of 5, and then we will compare how dynamic programming algorithm would compute Fibonacci of 5. Okay, so to compute Fibonacci of 5, we need to know the value of Fibonacci of 4 and the value of Fibonacci of 3. So to compute the value of Fibonacci of 4, we need to compute the value of Fibonacci of 3 and the value of Fibonacci of 2. And we continue on recursing until we get to the base cases, which are Fibonacci of 1 and Fibonacci of 0. Okay, so now we can compute this thing and we can compute this thing. So we can compute this thing, and we already know this thing, so we can compute this thing. But then again, we end up with this Fibonacci of 2, so we need to compute its value again. And now that we have these values, we can compute Fibonacci of 2, and we can finally compute Fibonacci of 4. But we're not done yet, because we have to go down this tree as well. So going down this tree, we get Fibonacci of 3, which is just Fibonacci of 2 plus Fibonacci of 1. But Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. And Fibonacci of 1 we already know, so we know this thing, we know this thing, we know this thing, we know this thing, we know this thing. And finally, we can compute Fibonacci of 5. Now, I want you to see how much problems we've solved repeatedly. Like for instance, we've calculated the value of Fibonacci of 2 over here, and over here. And that's an overhead that we might not be willing to take. And the solution to this is the dynamic programming algorithm, which I will present in a second. Okay, so how will dynamic programming calculate the value of Fibonacci of 5? Well, we start off in the same way. We need to compute Fibonacci of 4, Fibonacci of 3, Fibonacci of 2, and then we've got Fibonacci of 1 and Fibonacci of 0. So the cool thing here is that we have this table in which we can store values. So we've got Fibonacci of 1 is equal to 1, and we've got Fibonacci of 2, Fibonacci of 0. Okay, so this will be Fibonacci of 0, this will be Fibonacci of 1 equal to 1. Okay. And yeah, so we do this, we know this, so now we know this, but now that we know it, we put it in our special table, and we've got Fibonacci of 2 equal to 2. Okay, so Fibonacci of 3 is equal to Fibonacci of 2 plus Fibonacci of 1, so we know this, so now we can compute Fibonacci of 3, but Fibonacci of 3, so we compute Fibonacci of 3, and we put the value of Fibonacci of 3 in the table. And then Fibonacci of 4 is Fibonacci of 2. But we know the value of Fibonacci of 2. The value of Fibonacci of 2 is just 2, because we have it in the table. So now we can immediately compute the value of Fibonacci of 4. So we know that Fibonacci of 4 is equal to 5. Why? Because 5 is equal to 3 plus 2. Okay, so we have this thing as well. Now all we need to do is compute the value of Fibonacci of 3. But Fibonacci of 3, well, we already have Fibonacci of 3, it's over here. So we just take its value and find a solution to Fibonacci of 5. Now notice that we've reused all of the Fibonacci of 2 values, so we never compute anything twice, which saves us a lot of effort in computing the recursive trees all the way to the base cases. So in the end, the naive depth-first approach utilized 15 recursive calls, whereas the dynamic programming approach utilized 9 recursive calls and utilized the dynamic programming lookup table twice. Thanks for watching, and please check out the link below to find the video for the tutorial on my dynamic programming system called Dynamo.